So our next speaker is Lei Yang from MIT, and he'll be telling us about Prism, which has to do with scaling Nakamoto proof-of-work consensus.
Oh, gosh. Right. Come on. Yep. Okay. Hello everyone. I'm excited to be here to talk about our implementation and evaluation of the Prism consensus protocol, which achieves 10,000 times better performance than Bitcoin. So this is a multi-university collaboration between MIT, Stanford University, UIUC, and CMU. And I'd like to thank my collaborators, Vivek Bagaria, Gary Wang, my advisor, Mohammad Alezadeh, David Xie, Julia Fanti, and Pramod Vishwana. So we all know that Bitcoin has very good security, but in terms of performance, Bitcoin is not that good, okay? Because Bitcoin can only process 7 transactions per second, and it takes hours to confirm each one of them. And we found that Bitcoin couples performance with security in the sense that Bitcoin ties those parameters together with one design parameter, the mining rate. So if we want to increase the performance, we found that you will suffer a lot in security and vice versa. So what Prism does is that we decouple the two. And we do that by doing a natural extension of the Nakamoto consensus protocol. And we do a deconstruction and we scale each part. And I'm going to talk about how we do that in a minute. And I like to say that the Prism protocol is a very natural and beautiful protocol. And so it's so simple that we implemented it in 10,000 lines of Rust in just about 6 months. So we are happy with the protocol and the implementation. So I'm going to show a demo here. Yeah, that's a good point. So I have just started 100 EC2 machines right before the talk, and I'm going to launch one instance of Prism on each of those machines. And we open source the code, so feel free to check it out on GitHub. Okay, let me continue. Okay, let me continue. In this talk, I'm first going to talk about the Prism consensus protocol, and then I will introduce our system implementation, and finally, I'll talk about the evaluation. So let's dive in. Because Prism is built on longest chain protocol, so I think it's necessary that we do a quick recap on the Bitcoin consensus protocol. So Bitcoin uses the so-called longest chain rule, where every miner will try to extend and mine on the longest chain. And when it's a fork, which happens when 2 blocks accidentally attach to the same parent block, miners will choose the longer fork. So basically, they always follow the longest chain. There's a very important parameter here called the mining rate, which defines, on average, how fast the miners are going to mine new blocks. And in Bitcoin, this is said to be 1 block per 10 minutes. Another important aspect of the Bitcoin protocol is when do we actually confirm a transaction. So consider the following scenario where I have a transaction which I care about coming in a new block. When are we going to confirm that? A simple thinking is that we can confirm the transaction immediately, but however, there's a problem because it's possible that an attacker is mining a private chain which, because the mining process is random, it's a Poisson process, it's possible that the attacker can get lucky and mine the first few blocks faster than us. And when that happens, the attacker is going to release this private chain, and suddenly our transaction is deconfirmed because it's no longer in the longest chain. And our transaction is gone forever because now we have a longer chain, and everybody is going to switch to that. So obviously, it's not going to work. And Nakamoto proposed a solution, which is instead of confirming a transaction immediately, we're going to wait for the transaction to be buried K deep inside the longest chain. And that helps because even if the attacker can get lucky for the first few blocks, it's very unlikely that the attacker can get lucky in the long run because, after all, the attacker has less mining power than us, right? So Nakamoto did the calculation in his white paper. He made a table, and when we consider that there is a 30% adversary, in order to get a 0.1% probability of being attacked, we have to wait for 25 deep. So that's 250 minutes. Okay, so now that we have learned how Bitcoin works, let's talk about the performance. So first, there's the throughput, which is how fast, on average, the Bitcoin can confirm transactions, how many transactions it can confirm in a given period of time. And this can be calculated by multiplying the block size, how many transactions are there in a block, and the mining rate. How fast are we going to mine those blocks? And then we have latency, which is how long does it take for us to confirm a transaction. And we can do that calculation by dividing the confirmation depth K we just talked about and the mining rate. Okay, so far it seems that we have a good solution to improve the performance. We can simply increase the mining rate such that we both get higher throughput and lower latency, or at least we can increase the block size such that we get higher throughput. However, that is not going to work because of forking. And if we increase the mining rate or we increase the block size, we'll get more forking. And that happens because forking happens when two nodes in the network cannot hear from each other quickly enough such that they accidentally both mine on the same parent block. And if we increase the mining rate, then it's more likely that two nodes will accidentally both mine new blocks within a short interval. And if we increase the block size, then it takes longer for the block to propagate through the whole network, and both will cause the forking to increase. And forking is bad because forking compromises security. And to see why, we can see that on the left, there are 6 blocks in a perfect chain manner, and on the right, still 6 blocks, but with a lot of forking. If we compare them with the same adversary, we can see that on the left, we're secure, but on the right, we're no longer secure. We're outperformed by the security because forking essentially reduced the honest mining power. How bad is it? So we did the calculation. If we increase the mining rate or the block size just by a little, we actually sacrifice a lot of security. So in summary, Bitcoin couples security with performance. So next, let's talk about Prism. As I said, Prism does decoupling in order to improve the performance. And the first insight we got was in Bitcoin, a block actually serves 2 roles. The first is the new block will add some transaction to the ledger. And second, more implicitly, a new block is also certifying all of these direct and indirect parent blocks. It's like saying the block and the chain I mine on is the one true longest chain. So the first row, proposing, is directly tied to the throughput, because the faster we can propose, the more transactions we can add to the ledger. And the second row is tied to the confirmation latency, because the faster you can vote, the quicker you'll get confidence in a transaction. So let's first deal with the throughput. We already saw that in Bitcoin, the throughput is limited because of a forking. So what if we have a structure that does not have even the notion of forking? And that's why we introduced the transaction block. So transaction block is mined by the miners at a high mining rate. But however, we don't assume any structure, any chain structure between transaction blocks. So we can mine very fast. We can mine a lot of them, but without fearing that we increase the forking, because forking does not exist here. Okay, then what are we going to do with them? We're going to bring them to order by introducing proposer blocks. So proposer blocks are lightweight blocks which only contain hash pointers to those transaction blocks. And the proposer blocks will be mined in the Bitcoin rate and chained together as a Bitcoin longest chain. And because we mine them slowly and they are small, so the forking does not increase, however you increase the throughput. And that's how we increase and that's why in Prism, we can achieve the physical limit of your underlying network without even sacrificing security. And I'd like to mention here that Prism is also based on longest chain. It's also based on proof of work. And a miner will mine two types of blocks simultaneously, and they will use the hash value of the block to decide what type of a block, transaction or proposer, it becomes. So now that we have dealt with throughput, I'm going to talk about latency. So to deal with latency, we first note that even after we introduce the proposer chain, the voting rate still doesn't increase because we only have one proposer chain doing the voting. So we're going to do this deconstructing thing again and separate the voting job from the proposer blocks. And watch this. I'm going to redraw this graph in this way. So for now, it seems that we just separate a proposer block to two parts. One only contains the hash pointers to the transaction blocks, and the green ones that we call voter blocks, they only contain the pointer we call a vote to the proposer block. And we no longer assume longest chain structure in proposer blocks, but instead we assume a longest chain structure like Bitcoin in the voter blocks. So far we have not improved the confirmation latency, because still we only have one voter chain, and it's very important that this voter chain is secure, so we still have to wait for 25 deep. Otherwise, the attacker can simply attack the voter chain, as they do for Bitcoin. But now that we have separated the proposing and voting job, we can introduce a lot of voter chains, for example, 1,000. And an interesting discovery is that now that we have 1,000 voter chains, we do not require each one of them to be as secure, because even if, say, the attacker can attack one of the voter chains with, say, 30% probability, however, it's still very low probability that the attacker can simultaneously target 500 of the voter chains. So that's why we can reduce the confirmation latency K in Prism without sacrificing security. In a recent paper we published in ACM CCS 2019, we mathematically proved that as long as the adversary has less than 50% power, Prism guarantees security and liveness and consistency as in Bitcoin. For throughput, Prism provides 1 minus beta times C, where beta is the adversary power and C is the underlying network throughput. For confirmation latency, Prism's confirmation latency is proportional to the underlying network delay D, proportional to the confirmation reliability we need, and inversely proportional to the number of voter chains. Okay, now seems that we have a very good theory. It looks promising, but we also want to understand how it performs in the real world. And the theory doesn't just tell us that, because first, we have to admit that the protocol is a little bit more complex. It's a little bit more complex than Bitcoin. And second, actually in the theory, we assumed a simplified networking model. And also, recall that when we describe the confirmation latency of Prism, we use the big O notation, so that it's just a proportional. We don't know the constants here. And finally, there must be some other bottlenecks than network. So what are those bottlenecks going to be? That's why we did a system implementation, and I'm going to introduce that next. We implemented Prism in 10,000 lines of Rust. The implementation uses the UTXO-based model and supports pay-to-public key transactions. And we have the code open sourced. So I'd like to switch back to the demo. Sorry. First, let's see this visualization. It gives you a better sense of how Prism works. On the left, we have transaction blocks being mined at a very high rate, but recall that there's no structure within transaction blocks. The proposer blocks will refer to those transaction blocks so that it brings order to the transaction blocks, because you can just trace the proposer chain down. And we have a lot of voter chains, which gives votes to those proposer blocks. So those are the voter blocks, those are the proposer blocks, and those are a lot of transaction blocks. And here's a dashboard of the running system that I just started like 15 minutes ago. This is the topology. We have 100 nodes, and every node will connect to 4 random peers, as shown in this figure. Here's the total number of transactions being confirmed, 54.3 million. This is the average throughput. This is the instantaneous throughput. I have just displayed like 20 nodes here, because otherwise the figure will be cluttered. And here's the average confirmation latency. This is the instantaneous confirmation latency. We can see that it's fluctuating because it's a random process. And finally, we have the forking rate, which is essential to the security. We can see that the forking rate is kept about 0.1 or 10%. So it's very secure. It's secure against a 45% adversary. Okay. Now that we have seen the demo, let me Okay, let's continue. We have seen that Prism achieves 70,000 transactions per second and tens of seconds of latency. And we did a comparison with other protocols, which I'll cover in a minute. So when we talk about a blockchain client, we're actually talking about 2 roles. The first is the blockchain client participates in the consensus. It receives new blocks, connect them together into chains, and also mine new blocks. And also importantly, it takes the blocks and produce an ordering of the transactions. So note the word ordering here. The Prism consensus protocol, the essential role is to order the transactions. And unlike Bitcoin, we allow like invalid or double spend transactions to be included in the transaction blocks, because we discovered that as long as everybody agree on the order, then they can individually calculate the UTXO set and remove those invalid or double spend transactions. So that's the job of the ledger keeping module, which takes in the ordering of the transactions and execute the transactions one by one to produce the final updated UTXO set. To be quick, to have a high throughput, we have to be quick in both functions. So after implementing the protocol, we learned that first, Prism is able to move the bottleneck of a cryptocurrency or a blockchain system from consensus to ledger keeping. And more specifically, the bottleneck actually lies in the SSD and the database for storing the UTXO set. And also, we learned that you must parallelize both consensus and ledger keeping in order to achieve a high throughput. So we did a bunch of optimizations. First, we use a so-called scoreboarding technique to parallelize ledger keeping. And we do the ledger keeping asynchronously from consensus in order to parallelize consensus. We also introduce a functional design pattern in our client, and we disable transaction broadcasting in order to get a high network efficiency. So I'm going to talk about the first two optimizations here, and the rest are all in the paper. First, I'm going to talk about the scoreboarding technique. Scoreboarding is used in modern CPU designs extensively to enable parallel instructions to be executed. So for example, we have 2 coins on the left, A and B, and 4 transactions on the right. And suppose that we have 2 CPU cores and we want to utilize them. So naturally, we want to execute 2 transactions at a time. So in a naive way, we start the first 2 transactions, and if, very unfortunately, the second transaction gets started first, then the second transaction will get through, but the first one will fail because the coin A has already been used, but it's against the ordering of the transactions, so that's not correct. For the next 2 transactions, since the 4th transaction depends on the output of the 3rd, so the 4th one cannot get through because they are started at the same time. So we also get false result. The scoreboard technique introduces a very short table called a scoreboard, which before we execute a transaction, we will note down what coin is this transaction going to touch, or going to use, or going to produce. And before executing another transaction, we're going to look up the scoreboard to see whether there is coin that we're going to produce or use already present in the scoreboard. So for example, before starting the first transaction, we're going to note A and C in the scoreboard. And we have another CPU core, so we want to do another transaction. We found that the second transaction is touching the coin A again, so that's conflict. We are going to skip that first, skip that for now, and execute the third transaction. So we found that they can get through at the same time. And then for the rest 2 transactions, we found that there's also no conflict between them. So we're going to execute them together, and we get the correct result. So our evaluation shows that, so the x-axis is the number of CPU cores we provide with the program, and the y-axis is how fast we can do ledger keeping, the throughput. We note that after our optimization, the client achieves almost a linear scaling in CPU cores, in the sense that it scales up to 8 cores, and beyond that, the performance is kept by the SSD and the database. Another important optimization is that we do ledger keeping asynchronously from consensus. So what does that mean? We noticed that in Prism, the ledger updates is very infrequent compared to how fast the blocks are mined, because recall that we have 1,000 voter chains. So each voter chain and each voter block individually is very unlikely to trigger some new transactions to be confirmed, unlike Bitcoin, where generally every new block will trigger some transactions to be confirmed. So with that, we don't do the ledger keeping every time we receive a new block, as they do in Bitcoin. However, we put it in an asynchronous loop from the consensus logic so that it runs within its own loop periodically. By doing that, we're able to remove a lot of locks in the consensus logic, and our consensus logic is actually global lock-free so that it can use multiple threads and multiple CPU cores to process the incoming blocks in parallel so that it can keep up with the high block rate. Okay, so finally, I'm going to introduce our evaluation results. We did the test, we did the evaluation in 100 to 1,000 AWS EC2 instances. And actually, those instances are very lightweight. They are actually less powerful than the laptop I'm doing the presentation. And we connect the nodes into the same topology as in the demo. It's called a random 4 regular graph. Every node connects to 4 random nodes. And we introduce a 120 millisecond propagation delay to each link between peers. And for every node, we set a 400 Mbps ingress and egress bandwidth limiter to emulate a real internet. So we did the following experiments. First, we compared the throughput and latency with Algorand, Bitcoin NG, and Bitcoin. And we test whether whether Prism can scale to more nodes, say 1,000 here. And we evaluated whether our implementation is efficient in CPU or bandwidth utilization. And finally, we evaluated Prism under different kinds of attacks. And I'm going to introduce the first and the third result here. So first we have Prism, which achieves about 10 seconds of latency and 70,000 transactions per second. Then we have the longest chain protocol, which is the protocol that Bitcoin uses. So we can see that the longest chain protocol couples performance with security. So that if you want to increase the block size in order to get a higher throughput, you have to lower the mining rate so that you get a higher latency. As you can see here, it's a trade-off curve, and you increase the latency, you can also increase the throughput. But if you want high throughput, if you want low latency, you have to pay the price in throughput. And we can see that even with optimization, so we optimize the parameters in the longest chain protocol so that it's actually much faster than what Bitcoin is today. But however, we still cannot be faster than 100 seconds of confirmation latency, and the throughput cannot exceed 10,000 transactions per second. Then we have Bitcoin NG. We implemented Bitcoin NG by modifying our code, and we see that Bitcoin NG achieves better throughput. However, the latency is still as the Bitcoin or the longest chain protocol, because it essentially uses the longest chain protocol for voting and for confirmation. Finally, we have Algorand. We run the public Algorand code in the same setup, the same instance, same topology. We found that Algorand is capped at 1,000 transactions per second, and its confirmation latency ranges from about 2 seconds to about 100 seconds. Then we evaluated the protocols in different security settings. So for example, we increased the security to 33%. We found that we only pay a little price in confirmation latency for Prism. And we don't lose any throughput, because in Prism, we decouple throughput from security. We see that we pay a huge price in confirmation latency for Bitcoin NG and Bitcoin. And finally, for Algorand, Algorand's latency will spike up to infinity if we try to increase the security to 33%, so we cannot test that. And finally, we also test Prism with even higher security settings. And for the resource consumption, we see that our implementation is very efficient in the sense that more than 75% of CPU power is used for the necessary tasks, such as checking the signatures and updating the UTXO set. And for bandwidth, it may seem that since we use 1,000 voter chains, it may seem as inefficient, but actually more than 99.5% of data is actual useful data, and only less than 0.4% is for voter blocks. So here are some takeaways. First, Prism does the deconstruction by deconstructing a block in Bitcoin into the proposing job and the voting job, and scale each part to approach the physical limit performance. And we found that we must parallelize everything, consensus and ledger keeping in a client in order to get high throughput. And we found that Prism is able to move the bottleneck from consensus to ledger keeping, and more specifically, the SSD and the database. And finally, Prism is a very simple and natural extension of the Nakamoto consensus. So here are some results. And so finally recall that Prism builds on POW. So it enjoys the benefits of a POW, but also pays the energy inefficiency. In the next talk, we're going to remove that deficiency. And here are some resources. Please feel free to check them out. And I'm happy to take questions.
Okay, let's play. We're running a bit short on time, but if someone has a quick question and Professor Tse is willing to give up a few minutes of his talk, then.
Every node can produce the transaction block, and it's possible that there are overlap transactions in the transaction block. And does the result also account for the overlap transactions? And also, how, if there are multiple chains, how this difficulty being adjusted to make sure that the network is not overrun?
Sure, that's a very good question. So for the first question, I would summarize it as spamming. So we actually thought about that problem because it's possible that, yeah, two transaction blocks may contain overlapping transactions, and we introduced a simple solution by adding a random jittering between mining transaction into transaction blocks, and we're able to show that with only a 3 seconds of the random jittering, we're able to remove 80% of spamming or conflicting transactions, and the details are in the paper. And for the second question, we used the cryptographic sortation so that what kind of a block ends up into is randomly selected, so the miner cannot control that. So basically, we only still have this one difficulty parameter, and to adjust, we don't need to balance between different chains or type of blocks. Yeah, that's true. So it can be solved by the same mechanism as in Bitcoin.
Okay, do we have another quick question? Okay, I have a very, very quick question, which is that the formal analysis of Bitcoin Nakamoto consensus by Pas, Simon, and Shalat involved a delicate dependency of the network delay parameter, how long messages can be delayed in the network, and the mining rate. Were you able to show that everything still works with that analysis, or is there further work to do on adapting that formal analysis to your setting?
Yeah, so actually that's the reason that we did the system implementation, because it's very hard to adopt a sophisticated networking model. And that's why we did the implementation to show how the real-world performance it is.
Maybe I can add a point here. That, actually, our analysis, our formal analysis, is the round-by-round Bitcoin backbone protocol paper. So we have not extended to the PSS model, but we should be able to.
I see, okay. So that protocol assumes no messages arrive in the next round, right?
Yeah, round by round.
Okay, right. Okay, let's thank the speaker and